The last time I spoke, we were talking about the disjointness problem. We discussed in some detail the proof of the information theoretic proof of this result, and so yeah, my plan for today is to see some applications of communication complexity in analyzing other problems in computational complexity. We'll probably have time just to see two such examples, but we'll see them in some detail. Okay.
I think it was 1/3 last time. Numbers are getting smaller and smaller.
Constantly.
Yes.
It's changing from the 1/2, 1/3 now to 1/4.
Yeah. So.
It's getting smaller.
Yeah. So this 1/4 will sort of appear in the omega here. So based on that. So.
This is tricky.
So, depending on the time we have, we'll talk about the application of communication complexity to formula complexity and to showing lower bounds in streaming. Okay, so both these are lower bound results. Okay. So you have a Boolean function f on n variables. And you want to build a Boolean formula for this. So a Boolean formula is a tree like this. But the only gates I allow are ands and ors, and the negations appear only at the leaves, and such a formula computes a Boolean function. And we would like to understand how efficient we can make this formula for computing a given function f. There are two measures. One is size, and by size, let us say we just count the total number of literals that appear in the leaves, or the depth. The length of the longest path from the root to a leaf. Okay. So for formulas, the depth and size are pretty closely related. So we'll focus mainly on depth today. Okay. So size is exponential in depth. Okay. So this is a problem of analyzing the complexity of a Boolean function f. Now it turns out that this is connected to communication complexity, and this connection is through what is called the Karchmer-Wigderson call it Karchmer-Wigderson. So here at the moment, there is only one input. And on that input, we are trying to compute the function. And in the Karchmer-Wigderson communication problem, there are two parties, Alice and Bob. I'll just tell you what their inputs are going to be and what they're supposed to do with them. Okay. Now, Alice is given an input x, on which the function computes is on which the function is 1. Okay. And Bob is given an input on which the function is 0. And what's their task? They need to find an index where x and y differ. X and y must differ because the output of f is different on them. And Alice and Bob, given x and y, need to communicate and determine. So now there may be multiple i's. So strictly speaking, this is not a function that they're trying to compute of their inputs. For the same x and y, there are multiple acceptable answers I. If the x and y differ in many places, you are free to provide any I. Okay. So this is what Karchmer and Wigderson and actually it was observed perhaps even before. So this is 90 and they observed that the communication complexity of this problem is exactly the same as the formula complexity of f. Okay. So once again, let me write it down and then. So the communication complexity of the Karchmer-Wigderson problem for f I mean the deterministic communication complexity and why is this true?
Minimum depth for f.
Yeah, so when I say depth of a function, I mean minimize over all formulas computing that function of the depth. Yeah. So, okay, yeah. So the minimum depth to compute f is the same as the minimum communication over the worst case input for this problem. All right, so this is an equality, but actually we will use this equality to show a lower bound on depth of f. Okay? That is, we will show a lower bound on the communication complexity of the Karchmer-Wigderson game associated with a certain function, and from that we'll conclude that the formula depth for that function has to be large. Okay. So that is, we will only be using this direction. In other words, we want to show that if depth of f is small, then there is a short protocol for this problem. And let us just verify that. It's a more or less straightforward thing. Yeah. Okay. So imagine we have a formula for f, and it has a certain depth. And I want to, so let's say the depth is d. And I want to show a protocol for that communication problem, which works with just d bits of communication. Okay. So how does that work? Feed the input x here and feed the input y. The output gate evaluates to different values. On x, it evaluates to 1. On y, it evaluates to 0. Okay? So when Alice observes this, she sees a 1 and a 1 feeding into this AND gate, whereas for Bob, at least one of the two gates is feeding a 0 on Bob's input. Okay? So all the AND gates are where it is Alice's turn to communicate. And the OR gates are where it is Bob's turn to communicate. Okay. So this, you can just turn this tree into the protocol tree, replace.
What is the other thing?
Is it the same?
AND gates are where Bob communicates.
Sorry, AND is where Bob, and OR is where it's Alice. I'm sorry. Yeah. So now Bob sees a particular 0. One of these two is 0. So Bob points Alice in that direction. Okay. And now it's an OR here, and Alice had once feeding into this OR, whereas Bob has a 0 feeding into this. So for Bob, both these must evaluate to 0. For Alice, at least one of them evaluates to 1. So Alice says, oh, go this way. There is some difference in our input in this part. Okay. And depending on whether it's an OR gate or an AND gate, one of them can make progress down this tree. And after d steps, they would have hit a leaf. And this leaf must be evaluating to a different value for Alice and Bob. And they have found the I where xi and yi differ. Is this totally obvious? Yeah. Okay. And this goes the other way also. That is, if you have a protocol, then you can somehow take the protocol tree and just like magically relabel Alice and Bob by ANDs and ORs, and it somehow computes the function. Okay, but that is not important for us today. Okay. Good.
Sorry, what did the second or the earlier result do? Clavette result?
No, they also observed this, but they didn't use it in as spectacular a way as Karchner and Wigderson did. Okay, and I think it was probably forgotten, but so the point is that this game goes by the name Karchner-Wigderson game, but it was observed before also. Okay. So I want to. So this is a general framework, but today I want to use this to show a lower bound for a particular function f. Okay. So the function f that I want to it's a special sort of function, and just tell you what this function is. So this is a function on graphs. Okay. So there are 3n vertices. So imagine that this graph, an undirected graph on 3n vertices, has been provided to you by means of its adjacency matrix. Okay? And we want to know if there is a matching in this graph. A matching means a set of disjoint edges, whether this graph admits n disjoint edges. Does this graph have a matching of size n? Okay, so this is a Boolean function on 3n choose 2 variables. Yeah. 3n choose 2 variables, and the final answer we want to know is 0 or 1. Yes, it has a matching of size n. No, it doesn't have a. Okay, so don't take these parameters n and 3n seriously. I mean, the general matching problem also can be shown to be hard using the same method, but it will be easier for me to work with these parameters. Yeah, that's the reason I stated it like this. Okay, so the question is this. we have this particular Boolean function on 3 and choose 2 variables. And we want to show that if you want to compute this Boolean function using a formula, then the depth has to be large. Okay? So the theorem that means if you want to build a formula for this, you will need linear depth. Question?
Are you doing monotone or?
Sorry, I'm doing monotone. So, yeah, monotone.
It would have been more interesting without.
I know. I'm sorry, I messed it up. Okay, so yeah, so there was one more thing to write here. My notes, which I forgot, and got everybody interested. Yeah. So, if f, so just I'll come back to this. Yeah. So, if f is monotone, then we can expect f to be computed by a monotone function. That is, there are no negations at the leaves. So any monotone function can be computed by a monotone formula. So we can talk about the monotone depth of f. That is the depth of the smallest monotone formula computing f. And the following thing is true. And I'll just write an M, and let me just explain. So what's the Karchmer-Wigderson game now? Alice is given an input on which the function f is 1. Bob is given an input on which the function is 0. Since it's a monotone function, these two inputs must have a position where Alice has a 1 and Bob has a 0. It's not good enough for them to find a position where they differ. They need to find a position such that xi is 1 and yi is 0. Bob has a 0 and Alice has a 1 in that position. Okay, and the same sort of translation continues to work, and this is what we'll be using. Now I'll start again. Yeah, question?
Just define what a monotone Boolean function is.
Monotone Boolean function is, that is, if you flip any bit from 0 to 1, the value of the function can't go from 1 to 0. So if you imagine the set of all inputs as this is the all zeros and this is the all ones, then the monotone function takes values 1 and is 0. So it's just the cube has been kept like this. So it's monotone. Yes, thank you. Please keep asking. Yeah, okay. So we'll show the monotone depth of matching is omega n. Okay. And how will we show this? We actually show that show that this depth is large, we can use this theorem and show that the communication complexity of the associated Kaczmar-Wigderson problem is large. And to show that this communication complexity is large, one second, I messed up. Show that this communication complexity is large, it's enough to show that this disjoinous problem has a large randomized communication complexity. But this was already done. So what we are doing is just an old-fashioned reduction. We will show that if you could solve this Kaczmar-Wigderson communication problem efficiently, then actually you could have solved the disjoinous problem efficiently. This is a deterministic protocol. Using this deterministic protocol, we will construct a randomized protocol for the disjoinous function. And this is where there is a slight novelty. This translation from formula depth to communication complexity at the moment is all deterministic. But it's a very beautiful observation that we can use the deterministic protocol for this problem and a little bit of randomness to arrive at a randomized protocol for the disjoinous function. Question?
I'm not familiar with this depth concept, but is there a connection between the depth and the computational complexity of the problem?
Yeah, so it depends on the model of computation. Yeah, so right now if I declare my model of computation to be formulas, then you mean the running time?
Yeah, running time.
Running time. Okay, so running time is related to circuits. Okay, so you might say that the size of the smallest circuit computing F is related to the running time. Okay. Now, the difference between a circuit and a formula is that we allow only fan out one in a formula. Okay.
Let's see.
But can't you run this in time d?
Sorry?
Looks like you can run this in roughly time d times n maybe, or something like this.
The protocol, but to compute the function, of course, you have to do a 2 to the d sized computation.
Inputs can be replicated.
Oh, sorry, yeah. Oh, none of my, yeah.
Oh, okay, right.
Sorry,
Right. Okay, of course. Yeah, then it's 2 to the d sized.
I guess you're not trying to say NC.
Yeah, I'm not, yeah. So there is a model of computation. So this looks like parallel computation, you can say. This depth corresponds to parallel computation. All right? Okay, so our purpose is just to show that any formula for this function, any monotone formula for this function must have large depth. Question? Yeah.
It looks like some of those xi are negated, but I thought the function was supposed to be monotone.
So this picture was drawn when I was discussing this, and I did not erase the negations when I came down here. But right now we are talking about a formula like this with no negations anywhere.
I guess my question is, if you were trying to prove a problem's NP hard,
Sorry?
can you use this kind of bound to prove a problem's NP hard? You give a low bound on the depth, does that connect to...
You could use it to separate
P and NP or something.
NC and NP. Like a circuit lower bound would prove that if you prove it for a problem in NP, proves that P is different from NP. But
Okay.
So just like NP, P, these are classes. Yeah, these are classes inside of P called NC. And if you want to know if there's a separation between, say, NC and P, then we would like to pick a problem in P and show that it doesn't have efficient formulas of a certain depth. Okay, and this is along those lines. But here we are making a restriction. We are assuming that the formula is monotone. Yeah. All right. So we'll just show this.
But the matching problem corresponds to a monotone function, right?
Yeah, matching problem corresponds to a monotone function, but even though the function is monotone, it is not necessary that the optimum circuit for it should be monotone.
And it's not, there's no lower bound on the actual depth?
Sorry?
Is there a lower bound on the depth, not m depth?
For general matching problem?
Yeah, just curious.
No, at the moment we don't know.
Oh, so m, sorry, I missed it entirely. Because the m is so small, now I realize that there's actually a new definition here. So m depth is the among all the monotone circuits, the largest depth. Or the smallest?
Smaller, yes.
Now I got it. But then there may be other implementation which could have smaller depth.
But might use negation even though the form.
Is monotone. Okay, okay. Now I'm completely understanding.
Yeah. So what do we have? We have Alice and Bob, and they have this is the disjointness problem, and they need to determine if S and T are disjoint. Is that clear? Yeah. So this was our disjointness problem, and what we are trying to show is that we can solve the disjointness problem if somebody gave us a protocol for the matching problem, for the Kachmer-Wigderson game, for the matching problem. Okay. Now, so given these sets, we'll have to cook up graphs that we want to feed to Alice and Bob, so that the graph that we feed to Alice has a matching. The graph that we feed to Bob doesn't have a matching, and somehow from their answer, we should be able to deduce whether S and T are disjoint or not. Okay. That's roughly what we are trying to do. So let me just quickly tell you how these graphs are to be built. So Alice builds her graph as follows. So there are these 3n vertices. So let me call this A1, B1, C1, A2, B2, C2, A3, AN, BN, CN. Okay. So I've at least got my number of vertices right. Yeah, 3n vertices. Okay. Now, the element 1 may or may not be in the set. Okay. If it is in the set, Alice puts an edge here. And if it is not in the set, she puts an edge here. Okay. This is a little bit of a hacky reduction, but just, yeah. Okay. So if the element is in the set, Alice will put the edge here. Otherwise, she'll put her edge here. Okay. Now, Bob, what does Bob do? So I'm going to do it in 2 steps. So right now, Bob also has the same vertex set, A1, B1, C1, AN, BN, CN. So right now, here Alice put some edges. Bob is not putting edges here. He's just marking some vertices. Okay, and then I'll build the real graph for Bob here. So right now I'm just marking some vertices, and which vertices to mark will depend on his set T. Okay, so if he puts circles, let's say around some vertices. So in each row he's going to put 1 circle, and if I does not belong to T, then he puts the circle here. And if I belongs to T, he puts the circle in this column. So look at the ith element. If it belongs to T, go to the ith row and then put the circle in this column. And if I does not belong to T, put it here.
So, Jaikumar, before you do the reduction, so what is the reduction supposed to achieve? So if they intersect, what are these pair of instances supposed to do? And if they don't,
I'll just sorry?
Am I jumping ahead in what the criteria?
Yeah. So the way I'm saying it, you're jumping ahead, but just in a moment we'll both kind of synchronize. Yeah. Okay. So let's just do this. So we take these sets and build this graph. Okay. So I promised to give Bob a graph. I have not yet given him a graph. I have just given him these vertices and some set of vertices which he has marked. Okay? Let's call this set of vertices U, those that have been marked. What's the property? Yeah. Suppose they both, Alice and Bob, both have the element. Yeah. There is an element I which is in S and also in T. Let's see what happens. Alice will put an edge here, whereas Bob will put his circle far away from the edge. That means this vertex will not cover this edge, yeah, in the sense of vertex cover. Whereas if either of them misses the element I, then the element that has been marked will fall on the edge. Yeah. So here's the statement I want to make. So hope I got this right. So if S and T are disjoint, then suppose a particular element is not in S's set, the edge will appear in the right column. So no matter where Bob puts his node, they will intersect. I mean, the vertex will cover the edge. Okay? The only case when you don't cover is when both of them have ones. Yeah? So it's maybe what I wrote is not correct, but something like this is true. Okay? All right? So we have sort of reduced not to the matching problem, but the so-called vertex cover problem. That is, Bob's set U covers Alice's matching if and only if the sets are disjoint. So now, yes, so the next step. I have to tell you Alice's graph and Bob's graph. Okay. So Alice's graph is this. Okay. So it consists of a matching with n edges. There's one edge in each row, n edges. Okay. Now what is Bob's graph? Okay. So Bob picks some vertex in his, let's call this V. Yeah. We might as well pick the first one. It doesn't matter. Okay. So picks some vertex V and considers this set U prime, which is U delete. Okay. So he leaves this alone and just considers the rest. Okay. And the edge set of Bob's graph is U prime cross product with all the vertices minus, I'll draw a picture. Alice has a matching, and Bob used to have this set U of vertices. So what does he do? He just drops one vertex, and all the rest he connects completely. This is Bob's graph. This is Alice's graph. Let's call this G. We call this H. Once again, we had a disjointness instance. We turned it temporarily into a matching and a vertex cover. This vertex cover I'm translating into a graph with edges. Okay. Now this graph clearly has a matching of size n, and this graph, this is U prime. That is, one of the vertices was dropped, and then we built this. Now this U prime does not have a matching of size n, because
what are the vertices of U prime again? How many are there?
Okay, how many are there? So in this, U used to have n vertices. One of the vertices I'm omitting. So U prime now has n minus 1 vertices. Those n minus 1 vertices are being connected to everybody else. So it's a pretty dense graph.
All the 2n, all the 3n.
So there are 3n minus.
You're dropping one, so it should be 3n. It should be 2n because
Sorry, what did I do?
there's 2n outside, n minus 1 for U prime, and the deleted vertex, which is the last one.
So there are 3n vertices in all, right? And there are these n minus 1 vertices in U prime, and they are connected to everybody else.
Including the one that you deleted.
Deleted more?
Yes.
So it's deletion not from V but from U prime, right? So V still has that vertex.
V still has that vertex.
Sure.
Yeah.
That would work. Yeah.
Sorry, yeah. Okay, yeah. So that's right. So the one that we deleted, I don't know where it appears, but yeah.
Is it connected amongst themselves as well, or sort of? There are 3n vertices total. There's a subset of n minus 1.
Correct.
And
Just a complete bipartite graph.
Complete bipartite.
how many vertices are in this picture? Are there 4n minus 1 or 3n?
3n.
So it's
It's complete bipartite with 2n plus 1 and n minus 1, adding up to 3.
You could also make that left portion a complete thing, but it wouldn't matter because it's a question of how many are you matching from the right side. There are only n minus 1 vertices. So, no, you can't do that. It has to. I take that back. Sorry, it has to be a bipartite graph.
I'm leaving it as a bipartite graph right now.
Right.
Yeah, once again, let me start. How many vertices did I shade here? N. Okay. I just removed the shading on this. So there are only n minus 1 vertices that are shaded. Those I call U prime. Okay. How many other vertices are there in the graph? 2n plus 1. Okay. I collect every vertex in U prime to each of these 2n plus 1 vertices. Okay. That is my graph H. Does this H have a matching? No, because every edge is incident on U prime, and U prime has only n minus 1 edges. Okay, so at least, I don't know what we are going to do with this, but it looks like the graph that has been provided to Alice has a matching of size n, and the graph that has been provided to Bob doesn't have a matching of size n. Okay. Now, we could feed this to this protocol that we have for the Kastner-Wigderson game, and it should come up with a certain edge. Yeah. Now, this matching has an edge somewhere outside. Yeah, because there is an edge which is not incident on this. Okay. Now, if in the original graph here, it was a proper vertex cover. That is, these vertices covered these edges. Then there would be only one such edge of Alice, which is in this region. The edge that was incident on the vertex V, which we just removed from there. That edge, now V itself has moved here, and that edge also is here. But if these vertices did not cover these edges, there would at least be one edge which is not incident on that vertex V, which is here. Okay, so there is this vertex V here. Maybe there is an edge, but there would be at least one edge which is not incident on V and also sitting in this part. Okay, so when we feed this particular graph, these graphs to this protocol, it has to come back to us with one of these edges. Okay. Now, if it comes back with this edge, we would immediately know that our vertex set U did not cover the edge. That is, there was an edge that was not covered by U, and since, in which case, so that's what we wanted to know. U, so we conclude that U does not cover Alice's matching, so S and T must intersect. Okay. However, it is possible that even though there was this edge, when we fed this to the protocol, it came up with this edge. And now this edge is incident on the vertex V that we deleted, so we cannot conclude that there was an edge that was not covered by U. And because all the edges that we are being shown are incident on our U. Okay. So here is, so far everything was deterministic, but I said that. So here is what they do. Alice and Bob, they had these graphs. They apply a random permutation sigma. So they used shared randomness, and they just permute their vertices at random. Okay. So this is cryptography. Yeah? So these two, as far as we can tell, are symmetrically placed. Why did this particular protocol choose this, or choose this over this? Well, maybe it is hardwired that way. The inputs were such that it wanted to choose this over this. But now, we apply a random permutation. So there is equal chance of choosing this edge and this edge just by symmetry. Okay, so this needs, nothing I can say will convince you. Yeah? Okay, so, but you apply a random permutation sigma and then feed it to the Karchmer-Wigderson game. And then ask if the answer, so you feed it to the protocol and it comes up with an edge. It has to come up with an edge because this graph doesn't have a matching, this graph has a matching. And we ask if this edge contains, V. So we applied the permutation, it came up with an edge, and it was this edge. We kind of undo the permutation and check whether it was the image of one of the edges that intersected me. If it did, then we say, okay, sorry, we cannot say that, that it does not cover. But if it so happens that it comes up with an edge which is not incident on V, then we know that that set U was not a vertex cover for this matching, for Alice's graph, and we'll be done. Okay, so I'll just stop here. Question.
So again, why after, maybe you have Riemann-Wigderson games in such a way, but they always just do it just to find an edge which is incident on V.
Yeah, but the protocol does, this particular protocol, when it gets a particular graph, it acts in a deterministic way and finds a vertex. Okay, Now, I'm going to apply a random permutation. Now, you can imagine that there is a permutation that switches this with this. Okay? So that the protocol itself is still working on the graphs. It's not taking the random permutation as advice and then doing anything. Okay? So, yeah, not saying it very well, but because there is randomness, it is as likely to pick this edge as this edge.
So you can find the vertex V, right?
He cannot find, he doesn't know which is vertex V.
But like if this protocol like says see all the vertices,
yes.
Let's assume a very simple protocol. He sees all the vertices, and then he'll find the vertex which is. So they just share all their data, and then the protocol just looks. He knows which vertex is V, and he outputs this vertex.
But he doesn't know which vertex is V.
But you know, if you will share all the data.
Well, I don't. So, Alice and Bob, while they are trying to solve the disjointness problem, yeah, they pick this random permutation. Where did my sigma go? Yeah, there was this permutation sigma. This Alice and Bob keep to themselves, apply this permutation, and then feed that permutation to the protocol.
Yeah, but like let's say that correction Wigderson protocol, what he did, say he just exchanged all the data, all the graph.
That's right.
And then he looks, when say Alice knows which is vertex V, which is not belong to this itself U prime.
Yes.
You can find it. And then he can just output edge which is V. So
yeah, but if there were two edges, which were missing, that is.
Yeah, but he doesn't look on which edges are missing. He doesn't care about which edges are missing. Only he wants to mess up your argument.
No, I understand. Yeah, yeah. I think you're helping her too. Yeah, yeah. So go. Yeah, please go ahead. Yeah.
So in this case, he found the edge which is vertex V.
Okay, let us call vertex V as B1 for the moment. Okay.
He finds which is so after he gets all the graph from Bob, Alice knows which is B1. And then he outputs edge which belongs to B1.
Okay, so there are two Alices and two Bobs, right? Okay, so there is the Alice. No. Sorry, didn't mean to confuse you. This is the Alice and Bob of the disjointness problem, and these are the
Alice prime.
Alice hat and Bob hat of the Karchmer-Wigderson problem. All right? Alice and Bob of the disjointness problem apply the sigma, build their graph, and feed only the graphs to this.
Yes.
So now, just one moment. When I apply sigma to this vertex B1, it has gone somewhere. Okay? This Alice and this Bob are free to share their inputs, do whatever they want. They will not know which vertex corresponded to B1.
Not only, but they don't know that I mean, it just looks equivalent to all the other 2n plus 1 vertices. That's sort of.
Yeah.
Okay, great.
That's why I said I'll not convince anybody. Yeah. Okay. Yeah. Good. Yeah. So, question. Sorry, I didn't see.
So you're saying that basically, like, let's say for example, Alice hat and Bob hat have the protocol where they just share the graph and then they iterate over the edges and find the first one that doesn't.
Yeah.
Right. And then if you rearrange the edges in some arbitrary order, they'll find a different one first. But let's say they have a protocol where Alice hat and Bob hat say, well, here we have the edges we have the vertices and the edges that we were given. Now we look at every edge, UV, and we see if it's present in Alice and not present in Bob. And if that's true, we also check whether, for example, vertex U has at least degree 3, or vertex U is part of a 5-click, or vertex U has, or like this graph is isomorphic to this very particular graph or something, right?
That's right. So that induces a bias. Yeah.
Yeah. So then.
But I understand that in a general graph, permutation doesn't imply that every edge will appear, with equal probability. Look at the graphs I'm building. This is just a bunch of matchings. This is a bipartite graph, complete bipartite graph. Yeah, and there are these some edges which are located as matching. Isn't this completely symmetric? There is those special, features like 5 cliques and local trees or whatever are not present. This edge, and this edge, they are all. This is what like Alon talked pattern. The pattern is the same. Yeah. So if you permute them, this needs some convincing yourself, but it's really beautiful. Once you. Oh, I'll stop. No. All right. So I have 5 minutes. Yeah. So let's talk about the other application and see what happens. Okay. Sorry, I didn't mean to stop the discussion. If you want me to say more, I can.
But I mean, in the end, so what you did is, the result is that you get probability that if you find the edge which is incident to u,
little v, yeah.
Yes.
So yeah.
Okay, so if S intersect T was empty, then you would the probability that this doesn't happen, right? And if S intersect T was not empty, then this would happen with probability something like 1 over n.
No. Half, because maybe there are just 2 edges. It sometimes picks this edge, sometimes picks this edge. Half. Now I said 1/4, and you just repeat this protocol a few times. Don't worry about it. I mean, yeah. So errors are.
But this is also a one-sided error.
It's a one-sided error. Yeah. If you find that edge, then you know that that special vertex v that you deleted did not cover some edge, and then you're. Let you just think it over. Yeah.
Jaikumar, are there more robust versions of this argument where you have a gap in the matching sites? You want to approximate the matching sites? How delicate is it? We can take it offline.
Yeah, I'll take it offline, yeah. Just want to, in the time that I have, I'll just be able to tell you the problem and a lower bound that can be proved for it using communication complexity, and I'll tell you which problem the reduction is done from. Okay. So the problem is the following. You have a string here of k+1 elements from some alphabet. So each of these AIs is an element of capital sigma. Okay. And yeah, so Alon said we should remember that K is the size of the alphabet. Was that what he said? Anyway, for us it is. Okay. So yeah. Yeah. Sorry. Yeah. So yes. All right. So you have a stream here which has k+1 elements, but they come from an alphabet of size k. So some letter repeats. Yeah. And the goal is to find out which letter has repeated. Yeah. So, and we want to do this with small amounts of space. That is, you have a computer, and this data is going in front of you, and you have a small amount of space. You can't keep the entire string with you. Okay? But if you have k+1 elements, then you would like to say that, oh, this element repeated. Okay. Now, if you try to do this deterministically, basically you can't do much. Yeah? You will need space omega k. But there is a randomized protocol. With space actually, so Parikshit and I, we worked on this at some point, and we had a log cube algorithm. But the improved log squared k algorithm is due to
And where is the order of log algorithm, right?
Sorry?
Where is the order of log algorithm also?
We are allowed only one pass. So we don't no, so the point is that log k squared is a lower bound for this problem. But right now,
the log k one is the one where exactly one element appears twice and the remaining appear exactly one time. But here you're allowed other inputs where something can appear 3 times or 4 times.
so turns out that whenever you have situations where there is limited memory, yeah, you can turn that into some sort of a communication protocol. That is, if you have an efficient streaming algorithm, then that implies an efficient communication protocol for an associated problem. Okay, that is, you could perhaps cut the input into this part and this part, give this to Alice, give this to Bob, and since we are doing only one pass, tell Alice, you do all the work for the first half of the time, give me the data, and then I will continue, I being Bob, for the rest of the time. Okay, and how much communication does Alice have to do? Well, as much as the space complexity of this problem, because she just conveys to me the, what's it called, the state of the algorithm, and I continue from there. Okay, so if you could show that the associated communication problem is hard, then you would have shown that the streaming algorithm requires large amounts of space. Good. So the problem that you can probably try and to understand why such a protocol might exist, I'm just giving you a communication problem here. It is like set disjointness, S subset of n, T subset of n, but the size of S plus the size of T, yeah, is say, yeah. Now, when this happens, S and T definitely share an element. There's a guarantee, there's a guarantee coming out of just their sizes that they must share an element, and Alice and Bob need to find that element. Okay, so find I belonging to. This is the communication problem, and one round, Alice just needs to send a message to Bob, and Bob should be able to figure out what is the element that is common to them. And if you allow yourself randomness and some small amounts of error, then actually you can do this with order log squared k. Ways of communication. I'll let you think about how to do that. Okay? Sorry, what am I doing? Yeah, k has turned into n. Yeah, I changed n to k just to bring alone into it.
He's working his talk. Oh, so you skip the k altogether?
Yeah, let's keep it as n now. Yeah, I'll otherwise keep making the same mistake. Yeah. Just 2 more minutes, I'm over time. I'll just tell you what it does.
Sorry, I think I missed it. Do you mind if you... So how does the space and the communication complexity is equivalent? Can you...
Yeah, it's not equivalent, but a lower bound for communication complexity implies a lower bound for space, as follows. Suppose you had an efficient streaming algorithm for this problem. Okay, so then I cook up a corresponding, sorry, why is Karchmer Wigderson still here? I cook up a different communication problem as follows. So that is, so you take these inputs, the first k/2 inputs, let's say, and give them to Alice, and the remaining inputs to Bob, and this particular streaming algorithm did something. Okay, then Alice and Bob simulate the streaming algorithm and come up with the same answer. Okay, so we would have given a streaming protocol, streaming algorithm, we would have come up with a protocol for some problem. Okay, now we independently show and that problem is hard anyway, hard in terms of communication. Okay, and from that I claim that we can conclude that the original streaming problem was also required large amounts of space, because if the streaming algorithm had been super efficient in space, then this amount of communication would have sufficed for the communication problem. I mean, yeah. So So let me tell you what the index function problem is, and it turns out that Johari et al. Used the index function problem to show this lower bound. Okay, and what's the index function problem? It's a very natural problem. Alice has x belonging to 0, 1 to the n. Bob, or we can even change this. Let's say Alice has and Bob has an index I in n. And Alice sends one message, and Bob needs to know the ith component. So Alice has a long string. Yeah, you can think of it as an array of length n, each of which has t bits. Yeah? And Bob has an index, and he needs to know this. And Alice needs to send some information. In the end, Bob needs to know only t bits. But you can imagine that if you want to accomplish this, Alice essentially has to send the entire input over. Okay, so what is known is that these are t bits. In order to solve this problem, even randomized with some reasonable probability of error, Alice has to send the entire input, even though Bob is interested only in one of them, and Bob right in the beginning doesn't know which, Alice doesn't know which one Bob is interested in. Okay, so I'm sure the point is that there is just too much entropy, and you have to send all of it here. Okay, this is called the index function problem. The augmented index function problem says that in addition to I, Bob is also given x1, x2 up till xi minus 1. Okay. That is, when Bob needs this, he already somehow knows that is given to him. So it's not independently generated input. Alice's input is generated uniformly, let's say, And then a uniform I is chosen, and Bob is given everything before that, and he has to find out what this is, and Alice needs to help Bob in doing this. Okay, good. So turns out that you still need omega n times t communication for this augmented index problem. If you set this up with n and t both as log n, then this number turns into log n squared, and that is the source of this lower bound. Okay? So they managed to show that if you could solve the stringing problem in less than log squared k communication, then you could have solved this augmented index function problem with words of length t and with of log n and array of length log n efficiently, but that requires log squared n communication. Okay, I don't have time to tell you more. Question?
Yeah, just this augmented. So this means that if xi minus 1 happens to be xi, then Alice now has a very efficient way of just saying, look at my previous input, basically.
Yes. Yeah, she could.
But that sort of won't happen.
That will, yeah, will not happen often. I mean, h of x is h of x1 plus h of x2 given x1, h of x3 given x1, x2, and so on. Yeah, I don't want to insult you more. Yeah. So if the message is small, then there will be a lot of residual entropy even after seeing the message about something. And this x1 to xi minus 1 is essentially what is being given here. So what appears here in our information theory formulas is appearing here in the input, and that's how you analyze this problem. So you can just write down entropy and get this done, but I'm really out of time. Question? Thank you. Yeah, thank you.
Thanks a lot, Jaikumar,
Thanks.
for
Sure.
so much work.
No, right.
3 days of work, 4 days of work. So any more questions? Concluding questions?
Anyone try to de-randomize this calculus with this?
Meaning a deterministic to deterministic argument. So it's one of those very pretty things. You had a deterministic problem, you turned it into a randomized problem and used a randomized lower bound to conclude something. Yeah, it's one of the gems, I think. Yeah.
And of course, therefore, it's a randomized lower bound.
Randomized. So yeah, so it's a randomized lower bound for the Kachmer-Wigderson game. But yeah, amazing.
Okay, great. Thanks a lot.